So we would like to give more details on the completeness of real numbers. And we would like to begin by discussing the convergence of bounded monotonic sequences. So first of all, let's recall that according to the completeness axiom, every non-empty bounded above set of real numbers has a least upper bound. So symmetrically, every non-empty bounded below set of real numbers has a greatest lower bound. Let's recall that if we're talking about a set A, then the least upper bound is denoted by supremum of A, or sometimes least upper bound of A. And if we're talking about a bounded below a non-empty set, then its greatest lower bound is denoted by infimum of A, or greatest lower bound of A. And the reason that we have this symmetry is that A is bounded above, if and only if negative A, and what we mean by negative A is all the opposites of the elements of A, is bounded below. And S is the supremum of A, if and only if negative S is the infimum of negative A. So by using this very simple operation of taking the opposite of a set, and we can even picture it, we see that we need to establish just the properties for bounded above sets. And so let's say that this is a set A and this is its supremum. Then if we take the opposite elements, we're going to get the so this will be negative A, and this will be the infimum. And we see that there is a perfect correspondence between the two. Okay, so we would like to now look at monotonic sequences. So first of all, let's recall the definition of limit, because we're going to use it in a second. So definition. We will say that the limit as n tends to infinity of the sequence an is L if for any epsilon greater than 0, there exists n naught in n such that an minus L is less than epsilon for n greater than n naught. So again, it's a good idea to have some pictures in mind. So what we really mean here is that if we take any interval surrounding the alleged limit of the sequence, then all but finitely many of the terms of the sequence will find themselves inside that interval. And if we take an even smaller interval, then we just have to exclude more terms, always finitely many, so that the remaining infinitely many are in that interval. So that's why sometimes people write that there exists an n naught of epsilon, implying that this n naught depends on epsilon, and as epsilon gets smaller and smaller, n naught should be getting larger and larger. So now we would like to show that so proposition every increasing sequence which is bounded above converges. Okay, and when we say increasing, what we really mean is that A1 is less than or equal to A2 is less than or equal to A3, and so on and so forth. And it is true that in the literature, sometimes if we have these weak inequalities, we call the sequence non-decreasing. So usually if we call such a sequence increasing and we want strict inequalities, then we would call it strictly increasing. And it's true that both of these terminologies are used, and usually people will just define them in every context. So in this context, when we say increasing, we mean in the weak sense. Okay, so how do we show this? So proof. Let an be an increasing bounded above sequence and let L be the least upper bound, so the supremum of its set of terms. So we take all the values of the sequence, they form a bounded set because the sequence is bounded above, and we take the supremum. Actually, we should note here that this sequence is not just bounded above, it's bounded, so it's also bounded below by A1. So we could even forget about the above. But in any case, we're going to show that the least upper bound of its terms is actually the limit. So we will show that the limit as n tends to infinity of an is L. Okay, so how do we do this? Well, fix epsilon greater than 0. we will show that there exists a knot such that if n is greater than a knot, then a n knot, then a n minus L is less than epsilon. So L is the least upper bound. L minus epsilon is not an upper bound for an. So again, it's a good idea to draw a picture. So we have an increasing, and we know that at some point we have this number L that is the least upper bound of the set of its terms. If we go a little bit to the left, then we don't have an upper bound anymore. That's what it means for L to be the least upper bound. And the fact that we don't have an upper bound means that we have left terms of the sequence on our right. So this means that there exists a knot in N such that a knot is greater than L minus epsilon. Then if N is greater than a knot, we have a very nice and pleasant series of inequalities. So first of all, we have that a n naught is less than or equal to a n, right? Because the sequence is increasing. On the other hand, we have that a n is less than or equal to L, right? Because L is the least upper bound of the set of terms of a n. A n naught, on the other hand, is greater than L minus epsilon. That's how it was chosen. And finally, L is less than L plus epsilon. So this tells us that an is between L plus epsilon and L minus epsilon for n greater than a naught, which actually translates immediately to an minus L being between epsilon and negative epsilon. And that means that the absolute value cannot exceed epsilon. Actually, it's strictly less than epsilon for n greater than a naught. And that completes our proof. So again, by using the opposite of a sequence, we can argue that if an is decreasing and bounded below, then it is convergent. Again, here the argument, either you do it all over again, but the easiest thing here to say is that if an is decreasing and bounded below, then minus an is increasing and bounded above. And if the limit of minus an is, let's say, L, then negative L will be the limit of an. And that takes care of decreasing bounded sequences. So in other words, what we come up with is the conclusion that all bounded monotonic sequences of real numbers are converging. And that's all. Thanks for watching.